This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into the fascinating world of weak signal digital communication in amateur radio, specifically the FT4 and FT8 protocols. These modes have revolutionized how hams connect, especially in challenging conditions.
Indeed, FT8 in particular has become incredibly popular, transforming HF activity for many.
It's remarkable how quickly it gained traction, but what makes these protocols so efficient and effective?
The key lies in a combination of factors: highly efficient message compression, robust error correction, and a cleverly designed modulation scheme.
Let's unpack those elements one by one. Starting with the message compression. The paper highlights that FT4 and FT8 transmissions always convey exactly 77 bits of user information. How is that achieved?
They use sophisticated source encoding techniques. The 77 bits are cleverly allocated. 3 bits define the message type, 8 possibilities in total, allowing for different message formats, from simple call sign exchanges to more complex context-specific data. The remaining 74 bits are for the actual user information, with the encoding details depending on the chosen message type.
So it's a flexible system that adapts to various communication needs. And how does this system handle the varying lengths of information, like call signs? Some are much longer than others.
That's where the cleverness really shines. Standard call signs are encoded in 28 bits, but for longer or unusual calls, they use hash codes. This allows them to represent even complex call signs within the 77-bit limit. The receiving software then uses the most recently decoded call sign mapping to that hash code, displaying it in angle brackets if a match is found.
That's a very elegant solution to a common problem in data transmission. It's all about maximizing information density within a constrained space. Let's move on to error detection and correction. The paper mentions a 14-bit CRC and an 17491 LDPC code. Can you explain the role of these components?
Absolutely. The 14-bit cyclic redundancy check, CRC, is appended to the 77-bit message to detect errors. If the CRC doesn't match upon reception, the message is deemed corrupted. The LDPC code then takes over, adding 83 parity bits to create a 174-bit code word. This powerful code allows for correction of errors, even in very noisy conditions. The code is specifically designed and optimized for this application.
So it's a layered approach to error handling, providing both detection and correction capabilities. This is crucial for weak signal communication where errors are inevitable. The next key aspect is the modulation scheme. The paper describes the use of continuous phase frequency shift keying, CPFSK, with 8 tones for FT8 and 4 tones for FT4. What are the advantages of this approach?
CPFSK offers several advantages. First, it's constant envelope, meaning the signal amplitude remains constant, which is beneficial for nonlinear amplification. Second, the use of a gray code mapping ensures that adjacent tones differ by only 1 bit, improving robustness against Doppler spread, which is a common issue in HF propagation. FT4 and FT8 also employ Gaussian filtering to further minimize spectral side lobes, allowing for efficient spectrum utilization.
The Gaussian filtering is a particularly interesting detail. It smooths the frequency transitions, reducing spectral splatter and improving spectral efficiency. This is essential for operating in crowded bands. How are the actual waveforms generated, and how does the receiver synchronize with the transmitted signals?
The waveforms are generated by summing weighted Gaussian smoothed pulses, each representing a channel symbol. The weights are determined by the channel symbol values. Synchronization is achieved using Costas arrays embedded within the waveform. These are specific tone sequences that the receiver uses to lock onto the signal in both time and frequency. FT8 uses a 7-tone sequence, while FT4 uses 4 different Costas arrays.
So these Costas arrays act as a kind of signature for the signal, allowing the receiver to identify and synchronize with it amidst background noise and interference. The paper discusses advanced detection and decoding techniques in WSJTX. Can you elaborate on the methods used to decode these weak signals?
WSJTX employs non-coherent block detection, correlating received waveform segments with locally generated waveforms. This improves sensitivity compared to single symbol detection, particularly in slow fading conditions. Different block lengths are used, N1, 2, and 3 for FT8, N1, 2, and 4 for FT4, to optimize performance across various channel conditions. A soft demapper converts waveform correlations into soft decisions for each bit, which are then fed into a hybrid decoder combining belief propagation, BP, and ordered statistics decoding OSD algorithms.
The use of multiple block lengths and a hybrid decoding approach is a clever way to adapt to the dynamic nature of HF propagation. It's all about maximizing the chances of successful decoding. The concept of a priori AP information is also mentioned. How does this improve decoding performance?
AP information refers to information already known to the receiver, such as the call sign of the expected responder. By incorporating this prior knowledge, the decoder can focus its efforts on determining the remaining unknown bits, significantly improving sensitivity. The gains from using AP information are particularly noticeable in more disturbed channels.
So it's like giving the decoder a head start, reducing the search space, and increasing the probability of a correct decode. The paper presents decoding thresholds derived from simulations. What do these thresholds tell us?
The decoding thresholds represent the signal-to-noise ratio, SNR, at which the decoding probability is 50%. These simulations, using various channel models, show the sensitivity gains offered by block detection, the hybrid decoder, and the use of AP information. The results highlight the trade-offs between speed and sensitivity, with FT4 being faster but slightly less sensitive than FT8.
The simulations used ITU channel models to represent real-world conditions. What are the key parameters of these models?
The ITU models consider two independently fading paths with equal mean attenuation and frequency spreads. The frequency spread is the most important parameter, determining the performance degradation due to Doppler spread. The simulations show that FT8 maintains a sensitivity advantage over FT4 in less disturbed channels, but FT4 performs better in highly disturbed channels with significant Doppler spread due to its wider tone spacing.
So the choice between FT4 and FT8 depends on the specific propagation conditions and the desired balance between speed and sensitivity. Let's discuss message sequencing. The paper describes a typical QSO sequence and the role of the AutoSeek feature in WSJTX.
A typical QSO involves a series of exchanges, a CQ call, responses, signal reports, and acknowledgments. The AutoSeek feature automates this process, parsing decoded messages to determine the appropriate response and transmitting it automatically. However, it's important to note that human intervention is still required to initiate the QSO and verify the details. The software prevents fully robotic operation.
This automated sequencing is a significant improvement for faster modes like FT4 and FT8, where the shorter transmission intervals require quicker responses. The paper also mentions multipass decoding and signal subtraction. How do these techniques enhance the decoding capabilities?
WSJTX can perform multiple decoding passes. After decoding a strong signal, it reconstructs the transmitted waveform and subtracts it from the received audio. This process reveals weaker signals that might have been masked by the stronger one, allowing for the decoding of multiple signals within the same frequency band.
This is a very clever way to improve the overall efficiency of the system, extracting more information from a potentially crowded signal environment. Finally, let's talk about the software license and the author's intentions regarding the open sharing of this information.
The protocol specifications are in the public domain, encouraging other developers to create their own implementations. However, there are restrictions. Implementations must adhere to the protocol definitions, robotic QSOs are disallowed, and the names FT4 and FT8 can only be used if these conditions are met. The WSJTX source code itself is licensed under GPLv3.
This approach balances the desire for open collaboration with the need to maintain the integrity and functionality of the protocols. The paper includes an appendix detailing the source encoding algorithms. What kind of information is provided there?
Appendix A provides the complete specifications for mapping human-readable message fragments to the bit fields within the 77-bit payload. It includes algorithms for encoding call signs, grid locators, and other information elements presented in the form of short Fortran programs that are available in the public domain.
This level of detail is invaluable for anyone wanting to implement these protocols in their own software. So in summary, FT4 and FT8 represent a significant advancement in weak signal digital communication for amateur radio. Their success stems from a combination of efficient message compression, robust error correction, and a well-designed modulation scheme. The open sharing of the protocol specifications, while maintaining certain restrictions, fosters collaboration and innovation within the community.
Precisely. The design choices reflect a deep understanding of communication theory and a commitment to practical performance in real-world conditions.
That was a great discussion. Thank you for sharing your expertise.